All right, we are at section 14.8, standing waves. We'll actually use some of this information on uh, Tuesday's lab experiment. Let's go ahead and share uh, the PowerPoint slide. Okay, if you recall, if you were there in class, I was able to vibrate the slinky back and forth until I was able to get a standing wave on the slinky, and that's what they're doing here. They've got uh, they're producing large amplitude standing waves because of the vibration of this little blade on this string. Um, so we're going to study standing waves. Um, Everywhere you see on that top A, everywhere you see an N, that's a node. There's very little movement there. Ideally, there should be no movement. You can see the node, node, node. And of course, there has to be a node at the anchor points at the end because the string's not moving there. So those are actually going to be always going to be a node. We'll see in if you have an open tube, if the tube is closed at one end, there has to be a node there. So nodes are fairly easy to figure out. But if you look at these, the uh, you can see that the parts of the string are moving up and down uh, in time and producing this standing waveform. Uh, so d is equal to 1/2 lambda. In other words, the distance is equal to half the wavelength. D from node to node, the distance from node to node is 1/2 of a wavelength. Um, Here we just have a half a wavelength. It's the fundamental. It's the first harmonic. The fundamental is referred to as the first harmonic. All you have is a node and a node and the antinode in the middle. This is the largest or this is the lowest frequency that you can get on a suspended spring like this. A suspended string. So the length is equal to this is a 2 times lambda lambda 1/4. In other words, from node to antinode is a quarter wave, quarter lambda, and there's two of them. There's two of them on either side of the antinode. So that ends up being um, lambda 1/2. And so lambda is equal to 2L. So the wavelength is twice the length that you have here for the fundamental. So the fundamental is equal to the velocity divided by lambda 1 is equal to the velocity over 2L. Well, remember that velocity was defined as the force over the uh, the the uh, density per unit length. So the frequency is equal to 1/2L times the square root of the uh, force divided by uh, the density per unit length, the force, the tension. I may have said frequency. The force is equal to the tension in the string. Okay, the second harmonic here, we're able to get, I think this is similar to the one I produced in the lab. You can see there has to be a node at the anchor points. There's a node in the middle, and there's antinodes, a quarter wave on either side of the anchor point. So here the length is equal to four quarter wavelengths. From a node to an antinode is a quarter wave, antinode to a node is a quarter wave, and so on. So we have four quarter wavelengths for lambda over 2. That's the second harmonic. So the length is equal to lambda over 2. It's a complete wave. So going through the same exercise, f of 2 is equal to v over lambda over 2 equals v over L equals 2v over 2L equals the 2 times f of 1. So 2 times f of 1 is the second harmonic. So let's just say it was vibrating at 400 hertz. Now it's 800 hertz. It's double. Third harmonic. You have what, 1, 2, 3, 4, 5, 6 quarter waves. There you go. L equals 6 times lambda 3 over 4 equals 3 times lambda 3 over 2. So S sub 3 is equal to the velocity divided by lambda over 3. 3v over 2L equals 3 times the fundamental. So if it were if the fundamental were 400, the second harmonic was 800, this would be 1200. Okay, let's okay, so the frequency is equal to n times the fundamental frequency, equals n over 2L times the square root of the force divided by the unit density, where n here is equal to 1, 2, 3, and so forth. Okay, the amplitude of the vertical oscillation of any element of the string depends on the horizontal position of the element. So you can see here, this is a nice, which is this? This is the second fundamental. The first fundamental would just be a wave going back and forth, but now we've got this wave going back and forth. This is actually the second harmonic on here. So you have standing waves on strings, on stringed instruments. This is what we use. Excuse me, excuse the dogs, ignore the dogs. Don't just ignore them. Okay, we'll go ahead and stop it there. Let's see. I don't think that there's any more I want to say on that. You know, you can vary the string by, I mean, you can vary the frequency by either tightening the strings with the little keys or putting a finger on the string. You're changing the length. So those are different ways of changing the frequency, the tone that if you want on a stringed instrument. And we'll stop it right there. Let's stop the share. Oops.